Thank you so much for this introduction. To give a brief about me, I have around 20 years experience working in this industry. And today I will talk about the usage of AI and machine learning in fleet management. The fleet management industry is always evolving. Back in 2019, there was a paper published by Volvo on how they can capture the telemetrics to improve the working of the machines. Till then, different industries in logistics and transportation took those learnings and from research papers and started to evolve, utilizing that fleet management system into their company. The transportation and logistic companies with integration of AI in fleet management opened a new possibility in this era. The business is supposed to increase from 8.1 billion currently to 19.5 billion by 2032 by the usage of AI technologies. The highlights being use of machine learning, LOT, and computing devices to enable predictive maintenance and intelligent routing optimization. Uh, think that most of the people today we use Google Maps to travel from one place to another. What if these things are used by a driver to deliver a product to a store? Suppose a store sends an SOS that they're running out of stocks for a specific product during a promotion time or during our season time. A driver can plan his route, he can predict by when he will reach, and that way that one can be fulfilled by the customer, end customer, by the company, or by the end store. So it really opened new possibilities. Stores can share their warehouses with different customers, different kind of people, and that's route planning make all these things possible. To summarize, like how we can use AI in fleet management, uh, let let's divide it into few compressive steps. One is predictive maintenance, where AI systems can forecast vehicle failures with up to 90% accuracy, reducing breakdowns and maintenance of cost significantly. Imagine a vehicle which is going to break, and if we can predict that, it will save company a lot of money because they can go and fix that vehicle rather than having a vehicle driver calling them from the mid of a note at night that okay, my vehicle had breakdown, I need a mechanic to be sent here, or my vehicle needs to be towed. So that helped companies a lot in predictive maintenance. uh, about fuel efficiency. This will definitely help in fuel efficiency because using AI, we can predict driver behavior, how much he uses his fuel in traffic. Uh, Future directions in this is that emerging technologies such as federated reinforcement of blockchains and EV-specific analytics can further enhance our system of data security and system fleet maintenance. Now let's look at the diagram here, how we can capture the data that can be utilized for the maintenance. Imagine in the left side of the diagram, we have a driver which have a telemetry device installed in his vehicle, which will send uh, data to different data providers. We will have different telemetric polars that will be capturing the data from different streams. We can route that to Kafka. We're using Kafka as a data stream because it is very fast. It can support around 100K streams per second, and we can route that to different databases, which can be in memory or which can be fast databases like Kinetica, maybe a MemSQL, which can aggregate the data in real time and then create some dashboards which can be controlled by a provider who will sit in his office to see, okay, where is my truck? What's my location? Is there any storm that is coming? Can I suggest a driver an optimized route to reach a destination? Apart from that, it will also send that office a remote diagnostic of the vehicle, how my vehicle is performing at this location. Do I see any issues? Do I see any issues in the brake or the tires? Do I need to ask the driver to stop at a certain point so that I can fix the issue? That will come from the operations hub. Apart from that, once a day have passed, that the data can be sent to an analytics hub where data scientists can use the data to see how the driver behaved during driving. Did he drive fast when there was a speed limit? Or easy using a different route than the planned route that is delaying my delivery. So all these things can be captured in this fleet management for better user behavior and better for the company. Let's look at the conceptual model. What we can do. Suppose there is a provider which leases his vehicle. So when we lease a vehicle, there are certain steps in that vehicle steps. One is that we go for agreement. We can buy certain products that vehicle get attached to a supplier for certain time period, and we also enter with the agreement with certain customers. All this can be controlled in this data model flow. The data will be in one location that can be used for predictive maintenance. In a real-time architecture, uh, how it will look. There are certain external data providers which will send us the data. We have Zoner, we all know about it. We have Samsara, that also is a provider. Verizon Connect, Cortex, Geotab, Trimble, Omnitrax. All these providers to these today, they are sending data to different industry collecting from the vehicles. We will implement a device in a vehicle, maybe in our fuel tank, maybe we can put a sensor in the speedometer, maybe we can check the tire pressure by putting a device, maybe we can check a battery health, and the data will be pulled and sent to a Kafka topic. Different applications will have different topic. We will be having a reading application which will be reading the data from different topics, and then using a data flow, any ETL tool, we can send the data to a data lake that will be stored for history purpose, into a data warehouse which will be used for analytics purpose. So we have different external data providers which support us using a polling device like Zoner, Samsara, Verizon Connect, Cortex, Geotab, Trimble, Omnitrax, Volvo. We can pull all this data using a Kafka topic and send it to applications. Real-time applications will manage something as a spatial data like MemSQL, maybe a Kinetica. Data version can be sent to any Databricks, maybe a Snowflake, and we can have built data lake built over Azure or S3, which can be used for analytics purpose. Uh, there are certain tools in Amazon. Of course, our product is mainly in Amazon. So I mentioned Amazon Health and Amazon SageMaker, which can be used for analytics purpose. All this data which we are sending from telemetrics, like the data from the battery, from the engine, from the fuel consumption, tire pressure, brake system, battery health, can be used by data scientists to predict whether my fleet is performing perfectly, whether they are following the proper route, whether there are any issues in the vehicle, and that can be used by the end users or by the company managers to predict what was my route optimization. In the next slide, I will talk about the APIs which we generally use in managing those vehicles. On the left side, I have a service called Locate Management, which will go and hit the API gateway to get the data and the real-time location of the vehicle, where my vehicle is located, how it is behaving, whether it's following the route. We can use the Markov analysis algorithm for it, where it will state whether what was the previous spot of my driver, what is the next spot of my driver, so that I can predict where my vehicle is going. And if I can get traffic data in real time, I can say how much time it will take to go to a warehouse. We can also have a vehicle finder API to locate the vehicle at a specific time, at a specific location. And if my vehicle gets stolen, this can be used possibly by different agencies, federal agencies, to locate my vehicle. That is the best use case these days. We see federal agencies locating a vehicle uh, that is stolen in US. Apart from that, suppose rental companies renting their vehicle, they can predict in real time where the vehicle was taken. If somebody is dealing in returning the vehicle, it can be tracked and we can get that vehicle without any difficulty. Then there will be an API that we have developed for proactive maintenance. Based on the pings, we can send an API request to the vehicle to ask it to return back to nearest service center. The driver will see that in the dashboard, through which he can He can take corrective actions and return it to the nearest service center. All this can be managed at the back end in a different kind set of databases. I have mentioned geofencing, unique location, actual location, not reported into location. This is something where the vehicle goes, which we have not planned. So we can store the database to warn the driver where he has gone out of the track or out of the road and taken the vehicle. Uh, Apart from that, we will have a dataset for unit UT current location, which will state the current location of the vehicle. Uh, Technologies that generally we use in this for CI/CD platform, we can use any general available technology. Uh, for better, currently we use Bamboo here for CI/CD. We have Bitbucket, we have Maven, we use Flyway, we have Jira. For deployment, use Amazon EKS or we use different in-house libraries. For UIs, we use Spring Boot and Spring Security. For containers, generally we use a Docker container here. Streaming, I already mentioned, we use the Confluent Kafka topic for streaming purpose. Analytics, it's a big ball game. We use Amazon EMR, Amazon Ethna, Amazon SageMaker, Amazon QuickSight. Data IQ also is evolving. There are certain cases where we can use data IQ for prediction purpose. Observability, generally we use Wavefront, we use and Logstash. What we do when we get the logs from different vehicles, we try to apply analytics to see whether all my components which I'm using for prediction are working properly or not. Uh, we use PagerDuty and SMS modifications to send real-time messages to the driver. So in short, with this kind of applications, what we have done is that we have revolutionized the fleet industry. Today, in real time, we can know where is my vehicle. I can plan my fleet, which route it can go. Apart from that, I can predict the shortage of my warehouses and route my vehicle according to that place. To talk more about optimization, uh, there will always be a high initial investment. Generally, industries these days they don't want to invest first more on this because the cost of sensors, infrastructure, AI platforms can be significant. Imagine that if we have put in an LLM to predict all this data set, it will be a huge data set running few GPU servers, and it will require significant investment and analytics cost for that. Whether a company is interested in doing so, it initially is a challenge. But in long term, this generally helps significantly for the industry to maintain a fleet maintenance. The next challenge that we will have is data quality and availability. The kind of data that we will get will be huge. It will be certain petabytes per day. To maintain the quality of the data in these cases is really difficult. Uh, we have to rely on certain high volume of data with high frequency, and the parameters that will be utilized for data quality should be significantly high and should be in real time. Generally, there'll be a lot of noisy and inconsistent data, which will lead to a lot of false positive cases. To learn about them, we have to go on a reinforcement learning shape, where based on the data set, we will learn new optimization technique and again implement it. So it will be a great, huge learning curve. It took us around 4 years to implement such a technology in our current company. Then there'll be complex implementation. You will need skills, personals like data scientists, engineers. There'll be a lot of system integrations because we will have a lot of third parties. Different systems talk differently. To integrate with different systems will be a challenge. Then there'll be training of drivers and maintenance. The AI model, as mentioned earlier, will need a lot of validation to remain accurate. Uh, there will always be environment changes. Right now, we are talking about diesel vehicles. Future is coming is electric vehicles. So all these electric sensors that are today with this diesel vehicle should also work with the electric vehicles. That will bring significant challenges. So it will be an ever-changing world. Apart from the technology, today We are using one technology, maybe a Spark, tomorrow it will be Flink. To evolve around with technology also a challenge in fleet management. You have to always be up to date. Cybersecurity risk. What will happen? Suppose your data gets hacked. What will happen if one of the sensors get hacked and turns rogue, which will send you wrong data? That will bring down my entire system, entire prediction system. That also requires robust security protocols to protect sensitive vehicles and operational data. Then there'll be scalability challenges. As we are dealing with petabytes of data, we need system that will support these petabytes of data. Ensuring real-time processing and storage at scale will be technically very, very demanding. False alarms. Uh, Overly sensitive models may trigger unnecessary maintenance and increasing cost. Imagine that my vehicle is sending wrong message that it is going to break down. I take that to a workshop and the salesman comes and says me, no, there is no issues with the vehicle. You get a wrong signal. That will incur significant cost. So we have to be very sure what kind of model we are bringing and what it will be predicting. Future scope. In the current state, there's still a lot of things that we can work to enhance this. We can add sensors in battery, voltage, ignition state, maybe at engine coolant level. Maybe we can add a sensor in odometer to see if it's functioning properly. We can put sensors in the speed so that the driver can maintain the speed. If he is going over speed at a certain signal, it can automatically control the vehicle and break it down so the driver can never go out of speed. Transmission of oil, if you are running low in oil, it can indicate the driver that you're running low on oil and route it to the nearest center where he can fill his vehicle. But imagine a battery vehicle driving on the road and the battery is low and the driver is unaware of that or driver ignores it. The vehicle will automatically send an alarm to the nearest operation center to ask the driver to route the vehicle to a nearest location where he can charge the vehicle. Otherwise, it will increase significant cost. So, in a sense, this industry is evolving and there's still a lot of things to do. So, that ends my presentation. I am open for any questions now.
I loved that presentation because it kind of showed the complexity of a lot of times people think, oh, this is kind of a fairly simple system. But when you showed all of the tooling and all of I loved as well the case studies that you gave of how you have to factor in if something gets hacked or if something, a faulty sensor. So can you go into a bit more detail? Because I'm not sure if I missed it or you explained, how do you, with your models, handle that situation where you might have like a faulty sensor or you might have a hack sensor? Because you said you have to care for that in your models to make sure it doesn't skew your output. But can you go into a bit more detail about how you actually do that?
Oh, it's a wonderful question, actually. Uh, a sensor generally sends me a throughput per second, which we capture in real time. So there are certain data points that we see. There are around 120 data points from a sensor when it comes to us and we read it. So a data point can send you a signal that, okay, my level of noise from this vehicle is at the threshold maybe at 16.1 level. I'm just making note the number. The next time it is sending me a signal that my threshold of noise of my sensor is at around at 14.1. That means within 1 millisecond, the noise attribution increase significantly. That's the reason it is sending me two void signals. At one time, we can say, okay, my vehicle deteriorated significantly, but we have a history algorithms which will go and check a similar pattern behavior of sensors which was faulted during a runtime, whether my current signal matches that frequency or it's beyond that threshold level, through which I can confirm, okay, whether my sensor is behaving properly or something is wrong in that. Then I need to dig deep and see what are the data points other sensors are sending. If other sensors are also sending different kind of data sets, which looks conflicting, I imagine that my vehicle data points are hacked by some third party for malicious content, and I can immediately disconnect that vehicle from my data set, from my Kafka topic. saving my algorithms to send distress signal to the operation center so that it will look like, yeah, all my vehicles are getting distorted with this noise. Hence the reason whenever I see this kind of prediction based on our threshold value and history machine learning algorithms, we will immediately disconnect that. Hope I answered your question.
That's really complex. Actually. It's really interesting how you've gone down to the engineering level to figure that out. And just in other complexity, I love looking at your kind of um, I guess your system architecture, where you've got all the different levels. One thing I did notice is because the first thing was it scared me. It scared me how much was there. But the second one was when I was looking at the data stuff. For example, I saw Mongo and DynamoDB and Snowflake, and like there seemed to be a little bit of I wouldn't necessarily say it's duplication, but were all of those points necessary? And why did you decide to kind of introduce different technologies where potentially you could have streamlined and used a single one?
Oh, it's a very good question, actually. Uh, when we talked about data, telemetry data, there's a huge volume of data. There are certain limitations where which data storage systems we will use. MongoDB generates very fast, so if I have to do some real-time predictions, that is best suited for it. DynaDB is kindly for batches, although it is very fast. But whenever you are getting more than 150 throughputs per second from a Kafka topic, we have seen DynaDB to slow down. So generally, we use that for batch predictions. Suppose something that which I can predict after a delay of 15 minutes, I generally use DynaDB. But whenever there's a near real-time prediction, we send the data across to MongoDB, which will retrieve my data into my prediction into few seconds. For other storage system, whenever there is a delay, like I run batch jobs a week or maybe a day, because those are cost effective to store data for a longer term perspective, I use them. So that's the reason you can see different data sets. It's kind of optimization between cost and what is required. If I create a large scale MongoDB system, it will be huge costly. It's expensive for the company. So we kind of done a permutation combination which system to use for that so that we can manage our cost as well.
Great. So it's kind of fitting your model with your kind of needs. That's great. But I just want to thank you once again for sharing because I thought that was really interesting, looking at it from the more technical side. Because we hear so many talks about oh, just integrate ChatGPT or AI into your systems. But I really love the example that you gave in the question as well about how do you make sure your model doesn't get polluted? How do you actually keep with all, as you were saying, that real time processing? If you can't keep up with the batch. Right? So just want to thank you once again, Pratim, for sharing.
But I thanks for the chance and I appreciate giving me opportunity to speak here. Hopefully I will speak more here. Thank you.